to invest some R&D into creating network equipment that would help be part of a security solution. We also went out and acquired some technology. So from what was Cabletron to Interisys, the product portfolio looks completely different. We still sell switches, we still sell routers, but now we sell intrusion detection systems. Now we sell encryption technologies. And all of that is integration. But also what I want to start off with is just a little bit of history, so that we can understand where some of these vulnerabilities and things have come from. And really the whole thing started back in 1945 with this delightful lady, Admiral Grace Murray Hopper, who first coined the term a bug. And that whole term, a bug, actually came from the first computer at Harvard University when a moth actually got in between one of the relays. So a bug in the system actually goes all the way back to 1945. Subsequent to that, 4 years later, a guy called John von Neumann, conceptualized the idea of a self-replicating program. In other words, a program that can continue to evolve, which is really what a worm is. Okay? It takes advantage of a bug, and it replicates itself and distributes itself across a network. Xerox actually created a program which was essentially a worm. What it was to go out and probe all of the computers in its network to look for idle computers, computers that weren't doing anything. But in the end, they took it off the network because it was difficult to control, and it was actually consuming a lot of bandwidth, which is kind of what we're starting to see now. In fact, we're definitely seeing it now with the concept of all of these worms. And then the very first PC virus, 1986, came out of Pakistan, a virus called the Brain. And then the very first worm, I don't know if anybody's mentioned it over the past couple of days, was the Morris worm. This was a guy called Robert Morris who, out of boredom, actually managed to to crash 6,000 computers on the predecessor to the internet, which was ARPANET. And basically, this was the first guy that actually got convicted and fined and given some kind of sentence as a result of what he did. But essentially what he did was he exploited well-known vulnerabilities in the applications that existed on the ARPANET. SendMail and Finger were the two applications that he exploited. And history is going to repeat itself again and again and again. So there's a whole load more examples as we get a little bit more up to date. 95, we start seeing microviruses. Then we see the very famous Melissa virus. I don't know if anybody got caught with that one, but I remember it very clearly when I was working back in the UK. And I remember getting all of these Melissa viruses and having to delete them and all these different things. 2000, we had the I Love You virus. Denial of service attacks. The NIMDA virus was a particularly sophisticated virus. This virus had 5 ways of replicating itself. It could attach itself to an email. It could insert itself over network shares into directories where it would find documents and execute itself every time somebody opened one of those documents. It could attach itself to vulnerable web servers so that when people went to those web servers, they actually downloaded the virus as well. Klesworm comes in. That's a virus that still exists today. It's very active on the internet. More denial of service attacks, and then this year, Slammer, Blaster, and all the variants. So, it isn't something new. It's something that has been going on since all the way back since the very, very first computer was ever conceptualized. The internet. Over 6 million people connect to the internet a day. Most of them are unprotected. And this is an interesting one, is that the software that the corporations use is the same software that the home user can use. So a hacker can get the software freely, particularly in this part of the country because you can get it very cheaply, for nothing at all. And they can test it on their home systems before they unleash it into the corporate world. So the commonality between what's available to the people working at home and the people in the corporations is a great vector for spreading these types of viruses. So if I look at a worm, we'll look a little bit about how these things can propagate. Typically, the bad guy creates a worm and will test it. He will then scan around looking for a machine that he owns. In other words, a machine that he already has compromised, he has control over, but it's not necessarily his machine. And then the owned machine will start scanning all of the other machines to see if they are confected, and then the process continues. Now, If we had a firewall may in some cases actually protect you from this particular event or this particular virus. But take the case of a mobile user myself. I spend a lot of time traveling. I connect to the internet from a variety of different places, from a Wi-Fi hotspot, from a broadband connection in my hotel, from a dial-up connection. And I'm the sort of guy that can be very easily infected. So if I take my laptop and I come back into my corporate network, there's a very chance that I can infect the intranet again. And this is one of the problems that many, many corporations have, is how do we prevent our mobile users coming back into our network, even if we think we've protected the network itself from everybody else that's out there. So a quick lesson in Blaster. I don't know if anybody got hit by this, but this was, if you had Blaster on your network, you probably would have got this message to say that your RPC service has terminated unexpectedly. Basically, Blaster took advantage of a vulnerability that existed in RPC, and I think you've probably heard something about that already over the last couple of days. But the way Blaster worked was the attacking machine would look for a machine that had port 135 as an open and vulnerable port, and it would inject a buffer overflow, a bug, an exploit, into that system to gain access to that system. Then the worm would download the rest of the executable using TFTP. TFTP typically is a file transfer protocol, but renowned for being unsecure. There's no authentication mechanism for TFTP, but it can exist on the internet. Then the worm aggressively scans for all the other computers that have this vulnerability. And one of the key things about Blaster was that not only did it infect all these machines, but it was so aggressive in its scanning technique that it consumed all of the available bandwidth that was available on most customer networks. Again, firewalls could have prevented the spread. Personal firewalls could have also prevented that spread. So the impact of Blaster. Many systems crashed. It used TCP port 135, which is a Microsoft protocol meant for file sharing. But it should never really have been, there's not many applications that exist on the internet that require that. But for some reason, service providers do not block these particular types of ports, even though those applications have no business being transferred across the internet. And as I mentioned before, the aggressive scanning scheme actually placed a very, very heavy load on the network. So even though the Blaster virus or worm was a vulnerability in RPC, all of the other applications, your Oracle applications, your SAP applications, your customer relationship management applications, were affected as an indirect result of this particular virus consuming all of the bandwidth that was available on a network. Also highlighted user negligence, because the RPC vulnerability was announced way before the virus was actually released. And it actually just to highlight, that Microsoft did have the patches available, and it's pretty easy using Windows Update to download these patches. But what it did highlight is that people do not tend to patch. And I think what you've probably heard over those 2 years, of the next 2 days, is that patching becomes very, very important. So if we do get a virus, it's typically very difficult to eradicate it on a dumb network. And if I look at corporation networks today, they typically exist of a router at the core and a whole load of dumb switches that exist at the distribution and edge layers of the network. So, we need to have something a little bit more intelligent that can actually help to prevent these types of worms, these types of bandwidth abuses from actually penetrating into the network. So this is where we talk about secure networks themselves. So we don't talk about network security, because if I talk about network security, people think of intrusion detection systems, firewalls, VPNs. A secure network is a network which plays a part as the security infrastructure. In other words, the network itself operates as a system that covers every point of access to the infrastructure and can enforce, detect, and prevent certain things from happening. So the business case for secure networks, well, I think it's pretty obvious based on the discussions that we've been having, but security breaches affecting 90% of businesses, costing 17 billion annually. I mean, these figures are there. Everybody's familiar with SQL Slammer, Blaster, how the impact of that was. And Denial of service attacks were responsible for 33% of financial losses for 2003. And the dynamics of the world has changed. I mean, last year when I came to KL, I couldn't actually find a Wi-Fi place anywhere. Now I can go downstairs to the Citadel Hotel, there's Wi-Fi access. There's also in the mall, there's Wi-Fi access. In my hotel, there's Wi-Fi access. There's many, many more places where people can connect to the network. The dynamics have changed dramatically. So Secure Networks is there to give a consistent management interface, easier deployment, and to reduce the dependence on security expertise. Now, we've seen a lot of security experts today, but it is not every corporation that can afford to maintain their own security team. So we believe that customers will invest in a network solution that helps them to reduce things like capital expenditure and operating expenses simply by having the network itself, which they're going to invest in anyway, participate as part of the security solution. So the information infrastructure looks very much like this. You have different types of users who connect to the LAN, the wireless LAN, the WAN infrastructure, whether they're corporate users, remote users, and in some cases, strategic partners. We're seeing more and more that we have to let our partners, the people that we do business with, maybe they're our customers, maybe they're business partners, give them access to our resources, give them access to our network. And the network security sits somewhere here between the network and systems management and is there to perform detection and protection. Not to be confused with information security. Information security is there protecting your business applications. It's the authentication mechanisms for accessing your file servers, your business application, your CRM tools. Now, historically, network security was a bolt-on approach. In other words, we have a problem, we're going to buy a firewall. We have a problem, we're going to buy IDS. Now, those are very, very important tools to be part of a security solution, but they are kind of added on afterwards. And they're typically deployed, at choke points. So there was a penalty to pay for introducing these devices because they were, where the network traffic aggregated, we would put a firewall. Okay? So performance was compromised is at an expense to putting in security. So network security, this area here, like any security thing, is a policy. And it is not a policy, it is a cycle, it is a circle, it is something that never ends. And it starts with prevention, and it goes all the way around to assessment, detection, and response, and it is a never-ending cycle. So the first step is to actually implement some kind of prevention techniques, to deploy a policy that is consistent with your corporate goals. In other words, people within a corporation have different access rights, different requirements of different applications, and we need to enforce those policies, but this is the key. The key to this is that the policies are enforced at the edge of the network. The edge of the network is the point at which the user connects to the network itself. Now, if I think about any security model, any security model in the physical world or in any other world, security is enforced at the point of entry. When I arrived into KL, I came in on Thursday, as soon as I got off the airplane, what was the first thing I had to do? I had to go to immigration. I had to present my passport with my picture. I had to authenticate. The next thing they did was they stamped my passport and authorized me to come in for 30 days. They didn't wait for me to get to my hotel. It was done at the point at which I entered the country. If I make a financial transaction at the bank, I have to still present credentials. I have to put a signature. Okay? Everything should be done before you get into the system. But the network has been the opposite way around. It's been done at the core. And when people connect to your corporate networks, there's nothing to stop them connecting. Okay? It's a very, very wide open system, very, very wide open solution. So prevent, but prevent at the point at which the users connect. Okay? Response. If we do see something, if we do detect something on the network, the ability for the network to have the intelligence to respond to that particular event. So that could be a firewall reconfiguring itself. It could be enforcing rate limiting tools to prevent denial of service attacks. But before we can respond, we need to have some method of detection. This is where the intrusion detection systems come on, where they're looking for people doing things that not necessarily could be malicious. It could just be misuse of the network, because at the end of the day, misuse of the network also costs a corporation valuable money. Okay? And then the assessment side, the ability to assess the problems, the things that we have seen, and feed that back into the cycle so that we can make sure we can prevent it from coming again. So the secure networks is a full cycle security solution. So one of the first things, I mentioned that security must be enforced at the edge of the network. Now, part of being able to do that is the introduction of more intelligence into LAN switches. LAN switches traditionally have been pretty dumb devices. They would take information in, they would switch it to another port, and that was all they cared about. However, advances in silicon has meant that we can create switches that have the ability to classify packets of data as they enter the switch, and then once they classify them, we can do certain things with them. So if a user was to transmit a packet into the switch, we can start to look and see, well, where's that packet going? What's the IP address? What application is it part of? Is it a HTTP application? Is it an SAP application? Is it CASA? Is it somebody downloading files? Is it peer-to-peer networking? So once the user sends that in, we can have the switch analyze those packets of data against some pre-configured rules that says, okay, if you see this packet, I then want you to perform an action. And that action can be, do I deny the packet? Do I permit the traffic? Or do I rate limit the traffic? Do I give it a priority? So the intelligence in the switches is the ability to take the information that's transmitted by the users and do something meaningful with it. So why is this important? Well, historically, that was a function of the router. That was a function where you created different subnets, and every user existed on a different subnet, and we would put in an access control list to define what the rules were of what one subnet could say to another subnet. By introducing this into the LAN switch, we actually bring the access control to the edge of the network where the users connect. And we can deliver this independent of VLAN topology. Historically, VLANs were created to create different subnets, and then we provided access control in between those different subnets. But we still had to maintain a VLAN hierarchy. So access control, rather than being performed at the subnet or VLAN level, is performed at the switch level or even the port level itself. And in this way, we can actually prevent any unwanted traffic from ever entering the network. So what sort of things can we prevent using this? An example would be OSPF. Okay? OSPF is a router protocol, and if someone was to play around, plug in an OSPF-enabled router onto your network, it's going to screw around with your route tables and cause a denial of service. Now, no corporate user should ever have cause to require the OSPF protocol to enter the network at all. So we create a rule and says, block OSPF. I never want to see OSPF on my network unless it comes from one of my predefined routers. There you've prevented a denial of service attack. There's a lot of legacy protocols that users can simply turn on through ignorance. Okay? Windows is very easy to enable different protocols, but on the networks that some customers I speak to, they say, sometimes the network just gets slow, and then it recovers, and we don't know why. Now, there's a lot of noise on those customers' networks. I can speak to those customers' networks and these network administrators, and they say, yeah, I'm pure IP. I have nothing else but IP. You put a network analyzer on there, you see IPX, you see AppleTalk, you see all these other sort of protocols, which are very broadcasty protocols. They can consume a lot of bandwidth on the network. If we eliminate them from the network completely, then we never have to worry about that being a problem. We never have to worry about that causing a network slowdown. Other protocols, SNMP, Telnet, FTP. In the case of Blaster, TFTP. TFTP is typically used by network devices to do firmware downloads or software updates. But your average user never needs to use those protocols. So if we can eliminate them from the edge of the network, we eliminate people who are connecting to that network ever from being able to use those particular protocols. DHCP. I don't know if anybody in this room has ever configured a DHCP server and then connected it to a corporate network. I did it once by mistake. I was in the lab, I was playing around with DHCP. I took my laptop, put it on my corporate network, and then all of a sudden it was my laptop that was answering all the DHCP requests from everybody else in the subnet. So I went out to a meeting, I left my laptop there. The IT guy's going crazy because he's going around and he goes, nobody can do anything. But every time I look, they've got an IP address of 192.168. That's not our corporate, DHCP address. I went, oh shit, yeah, sorry guys. Unplugged my laptop, network came back up again. But I was out for a day and he could not find that problem. And I've been to universities, I've been to software houses, I've been to corporates, and this is a big problem for them. Because if somebody does introduce a DHCP server on the network, it can bring down an entire network. And it's not that difficult to do. And it's not something that an access control list will actually prevent. So I create a rule that denies DHCP servers existing on the network. Protected IP addresses. Certain routers and servers have static IP addresses, which some users should never actually be able to talk to. So I can create rules to prevent that from happening. I can also prevent rules from users creating and configuring their own servers. One of the problems with them creating their own servers is that corporation has no control, no management over those servers. So if I can create rules that prevent, say, anybody transmitting any network traffic with a source port of SMTP, source port of 80 for HTTP, SMTP, whatever, I can actually prevent rogue servers, rogue applications appearing on the network itself. And then worms and viruses, as we've already discussed, exploit vulnerabilities in applications, and we can create rules, which we have done for many of our customers, to actually prevent the spread of the worms and viruses from the likes of myself. The mobile user who comes in infected, if I plug into the network, I can actually create rules on the network devices themselves that will prevent that worm from propagating and spreading to other devices. Other prevention tools, classification and rate limiting. If I can classify an application, and then I can rate limit it. Okay? So, for example, ping. Ping is a tool to test connectivity. But every user in most corporate networks either has a 10 or even 100, or very soon next year, everybody's going to have 10, 100, or 1,000 connection to the corporate network. That's a lot of bandwidth. And imagine how much damage somebody can do with a denial of service attack tool if they have that sort of bandwidth and that sort of access to the network. But for something like ping, for example, ICMP, okay, we let the users use the tool. It's good to be able to ping devices. It's good to understand if I can connect there. But if I rate limit to an acceptable level, 64K, that's more than enough that any corporate user should be able to use a ping. So that's an example of how we can use classification and rate limiting to prevent how much bandwidth any particular protocol or application can consume on the corporate network. So as I mentioned before, where best to position classification? At the edge of the network. The policies are enforced at the point of entry, and I can't stress that enough. I've already stressed it once. So how do we configure this? Because if I'm going to start creating rules, and I'm talking about ports and things, 100 ports, 1,000 ports, 500 ports, that's a lot of configuration to do. And if you use a CLI, it's going to become very, very tedious. So, and it can also, create errors, misconfiguration. So we need an easy-to-use tool that allows us to create the different services. That allows us to define what it is we want to prevent on the network, what we want to allow, what we want to rate limit. Wizards basically give the service a name, decide what I want the protocol to be, how I classify it, and then define the action. Do I want to give it permission? Do I want to deny it? Do I want to rate limit it? And then once I've done that, I can group it into different folders. So I could create a global policy that says deny spoofing and administration protocols. So in this case, we've got discard OSPF, discard Telnet, FTTP, source port SMTP, source port 53, no DNS service. And then once I've created these services, group them into a folder, and then push them down to the network. So in this case, I use an enforce button, and what that does is that enforce will go out and push that policy down to either all of the ports, all of the devices that exist in the building. Kind of like a centralized architecture. I click enforce. That policy has been pushed down to every single device. Now, imagine you're under attack from a virus, and you want to prevent in the case of Blaster, remember, you looked at port 135, it did the download using TFTP, port 69. If I saw that was coming, if I knew that it was there, or even if it was already happening, I could, in one click, push down a policy that prevents port 135 and port 69 from the network. That gives me, the network administrator, enough time to make sure that I've patched all the systems to prevent that from ever happening again. But most importantly, my corporate other applications that don't rely on port 135 and port 69 will continue to function. Okay? That becomes a very, very key part of what a secure network should be, is the ability to react very quickly to those types of events. Okay, so the advances in silicon technology have enabled us to create layer 2 to layer 4 classification. The next step is also to authenticate the user before they come onto the network. As I mentioned before, when I landed at the airport, I presented my passport, I authenticated to the people that said, okay, you're allowed to come into Malaysia because I've seen your passport, I'll stamp it. Authentication becomes a very important part. So authentication ensures that any user or device is authenticated before they can access the network. Now, I went to a customer in Singapore last year, and before I went there, it was a very secure environment. I had to submit my passport details and the number of the car that I was coming in, and they met me at the gate, and I showed them my passport, and they gave me an escort, and the guy actually walked me all the way up to the conference room, and he left me in the conference room, and he goes, okay, you know, the guy they're going to meet is going to be here in about 10, 15 minutes. He's running a little bit late. So I'm sitting down there, and I goes, oh, man, you've got great security, you know, escorted all the way up here. And I look down, and I see there's an RJ45 port in the conference room. I said, what's stopping me from connecting to that port? They went, huh? I said, you got a network port there. Is it turned on? Is it patched in? They said, well, yeah, of course it is. Why would it be there if it wasn't patched in? So you're telling me that you left me here after escorting me and authenticating me and doing all these other things, that for 20 minutes I could have had complete access to your network? Yeah, that's exactly it. There was no mechanism for me to protect it. Now, what's in any building, forget if it's a government organization, what is the most secure part of any organization? It's a data center. You know, data centers have passcodes, they have, you know, security systems, they have things locked up. But the data center extends outside those walls and actually comes to an end where you actually plug in the PCs. But today, most networks do not authenticate users before they can connect. So authentication becomes very, very key to prevent unauthorized users from connecting to the network. So we can do that using Radius. Radius is very pervasive across, you know, most of the world. It's being utilized by ISPs to do authentication. It's a standard, and it's a very scalable system. So if we take Radius to help facilitate this authentication, but you know, we understand that the corporations have other directory services. They might be using Novell NDS, they might be using Active Directory, there could be some LDAP directory there, which already contains most of the information about the users that exist within that corporation. So the idea behind authenticating the user is to use Radius to facilitate the authentication, but still maintain the same back-end authentication system that already exists in most customer premises. So if I take the InterSys switches, we have various methods to do authentication. We can do a web-based login, MAC address authentication, or something that's a new protocol that was defined by the IEEE a couple of years ago is 802.1x. So I'm going to talk a little bit about how those mechanisms work. Web-based authentication, a user boots up his PC, and at the point at which he boots up his PC, as soon as he connects, the port is turned off. In order to log on, he brings up a web browser, and embedded in the switch is a very small web server that presents the user with a web page to enter his username and password, his credentials. So essentially, that's an embedded thing in the switch, and the switch will only allow any user access and enough protocol rights to access that web page. So every switch has an embedded web server. Once we put in the credentials into the web page, the switch passes the authentication credentials to a Radius server. The Radius then can either authenticate it by itself using a local database, but more probably will pass it through to some kind of directory such as Active Directory, NDS, or LDAP. Directory server says, yes, you're authenticated. The radius informs the switch, and the user's granted access. Okay? So web-based authentication is nice because most devices have a web browser on them anyway. Okay? So it's pretty nice. You don't have to have any other client in there, but not good for dumb devices like printers, for example. And also, it also requires that the user has to boot the PC up first. So it's not really a single sign-on because you'll have to boot up, log into his operating system, bring up a web browser, authenticate to the network, and it's kind of a, backward way of doing things. But good for public access areas, because if you've got guests coming into your network, if you've got different people coming into your network, if you're a university, for example, maybe you've got teachers, maybe you've got students, and you want to differentiate between the two. You want these people to authenticate, then this is a nice way to do that. MAC address-based authentication. Every NIC card, every network interface card has a unique MAC address. So one way we can do that is that the device boots and it starts to transmit data into the network. At this point, the network port is in the off state. The switch receives the first packet that's sent by the device. This enables it to learn the MAC address. Switch passes the MAC address to the radio server with a default password. Radio says, OK, you're authenticated, and the port transitions to on. This allows dumb devices to be connected, things like printers that don't have that much intelligence. But it does require the network administrator to maintain a database of all the MAC addresses, and that's very much complex, and most network managers don't really want to be able to do that. Also, it's not the most secure option. A MAC address can be spoofed. There's not great password protection in there either. So the third method is 802.1x. 802.1x was a protocol specifically designed for network devices to exchange protocol information. It does require that the end station has an 802.1x client onto the thing itself, but 802.1x is embedded with Windows XP. It actually comes as part of the operating system. And also Windows 2000 Service Pack 3 has an 802.1x client embedded into the operating system also. Other radius vendors, Funk, Meeting House, also provide these types of clients. But it really does provide the most comprehensive support for authentication. It leverages off the Windows operating system, so it gives you the single sign-on. You log into the operating system, your credentials are passed to the switch via this 802.1x protocol. So this really does provide the highest level of security, the most integrated way to go forward. So that's what the Microsoft client looks like. You double click on your network icon, you can bring it up, and it will tell you, okay, in this case, I want to automatically use my Windows logon name and password, if any. So the actual 802.1x protocol works in conjunction with Radius. EAPOL stands for Extensible Authentication Protocol over LAN. And there's an exchange between the switch, the Radius server, and the end user to go through a challenge response type scenario to enable the user to authenticate. So and essentially, the user PC boots up, the user logs into his operating system, so in much the same way that you would use any other Windows logon. The 2.1x protocol passes the user credentials to the switch. This can also include certificate information depending on what sort of authentication mechanism that you're actually using to log onto your corporate services. Switch passes it to Radius, passes it to the directory. Directory informs the user, informs the switch, and the user is granted access. So authentication actually provides a lot of control for the network administrator. It allows them to define who's allowed to connect to the network, who's not allowed to connect to the network. But Radius also introduces a load of other features depending on the Radius server that you use. Radius keeps logs of who authenticated, when they get authenticated, which port on which device they authenticated from. And that becomes important if you're looking back for forensic type stuff. If somebody did something on your network at a particular time, you can go back and see who was connected to your network, where they were physically connected, and at what time they were connected. You can also set time of day policies to say, okay, you can authenticate between 9 to 5:30. Anything other than that, you're not allowed access to the network. So there's a variety of different things that Radius can do. Most Radius servers are very nicely integrated with Active Directory and NDS. What this also enables is for this concept of user roles. And I'm going to talk a little bit about this, because if I can combine authentication with L2 to L4 classification, I become a very, very powerful network tool, because once I authenticate to the network understands who I am. Once the network understands who I am, he can deploy a specific policy unique to my business role. So combining L2 to L4 classification policies with authentication gives us the user personalized network. This allows an administrator to create different user roles and then map them to L2 to L4 classification switches. So in other words, a table of rules for each business role is distributed to every single switch in the network. Once the user authenticates, the correct policy can be applied to the port that the user is connected to. So Radius actually works with the directory to deliver the user roles to the switch. So this is Active Directory. Most customers will have some kind of directory in place that has different security groups that define the different business roles of the different people that exist in their organization. Then I can create different rules which mirrors that. I can have an executive role, a finance role, a marketing role, a sales role. And then using the different services that I've defined, using L2 to L4 classification, I can then apply them to the different user roles. So putting it all together, first step is to define the different policies, push them down to the switches using the enforce button. Then a user logs in using EAP or 802.1x. Once we authenticate, the directory and the Radius server can work together to understand what is your function, what is your security group, what is your role. So in this case, this person, Mary, authenticated, and I'm going to use the Radius server to come back and say, you're a salesperson. The switch will receive that. Classification is decoded. The switch will have a role for Mary, sales, that says, okay, you have high priority SAP, rate limited web access, you don't have access to SNMP. Basically, your role is defined as soon as you connect to the switch. And it's applied to the particular port. So essentially, if I can combine the authentication part with the layer 2, layer 4 classification part, what I've actually done is created a self-configuring network that is dynamically adjusting no matter where the user connects. So if the user connects to a switch in, say, the conference room, he's going to get the same level of service as he would do if he connected to the switch that's at his desk. Okay? So the user experience should be consistent. Okay. So that's the prevention, the detection part. The final part of all this is the detect and the assessment part. So Enterasys has a product, the Dragon Intrusion Detection System. If you're interested in seeing it, we actually have it monitoring the hacking competition downstairs, and it's been good fun to actually watch who's winning, because Dragon is giving us all the logs, it's showing us who's compromised, etc. So pass by our booth as you're walking out, and we can show you what some of these hacking guys were doing. But basically, Enterasys Dragon is a system which incorporates a variety of techniques to do detection on a network. So the first part of it is the network sensor, which detects network misuse and attacks that exist across the network. And it uses multiple methods. It uses signatures. Signatures, very much like a virus checker. A signature looks for a particular sequence of ones and zeros, essentially, in network traffic that represent either a known attack or something that looks like it could be an attack. However, there's other methods as well, protocol-based, the ability to decode protocols, understand if there's anything weird in there that might be representative of an attacker or a misuse of the network, and anomaly-based. Anomaly-based means something that's not quite right on the network. An example would be one workstation goes out and pings every other workstation on the network. That's not normal network behavior. You shouldn't be doing that. It's probably representative of a port scan. So placed at the network aggregation points, the best place to put an IDS, if you can think of it like a security camera, if I walk into the bank, I'm normally monitored by a camera. The camera doesn't actually do anything, it just monitors. So it's not actually processing the data, it's just looking at the data. So a nice place to put it is either, somewhere in the network where it can see all of the data that you want to monitor. Second component is the host-based intrusion detection system. These are agents which can exist on the web servers, the critical applications, to monitor and look for attacks that are directly targeted at the individual systems and applications. And again, this has multiple detection methods. It can be looking at log analysis. It can be monitoring the logs of operating systems and applications, looking for particular security events. It can be monitoring particular files and the integrity of files to ensure that nobody's changed those files. Looking for backdoor services. In a Windows environment, monitoring the registry services. So in other words, the HIDS is there to look for traffic patterns and on the host systems themselves. And then the final component of an intrusion detection system is the management system, to provide real-time feedback, forensic capabilities back to the user to understand what had happened on the network itself. So I've talked a little bit about, the LAN switches playing a part in the prevention, authentication. The detection part can be provided by an intrusion detection system. Now again, if we can combine all of that together, we can create a very integrated, very secure network infrastructure that can dynamically respond to particular events as and when they happen. So I use, in this case, a corporate internal user starts scanning for open ports on a DNS server. The Dragon will detect that activity, identifies the IP address or the MAC address, passes that information to the NMS, and the NMS can go out and probe the network to find out where is that user connected and which switch port is he connected to, and then enforce an automatic response. So the response can be, just log the information. Tell me which user on which port tried to scan my DNS server. Or stop the traffic at the protocol layer. Dynamically put in a policy that says, protect my DNS server from this one particular user. Change the policy of the user to a penalty box. In other words, take this user and just give him very limited access to the network until I understand what he's done. Or just simply disable the physical port. Remove all access rights for that particular user. So secure networks is very, very tight integration of the classification services of the switches, the authentication services of Radius, the detection services of intrusion detection, and combined together can create a very dynamic, active response to a corporate network. A couple of case studies. SAP is one customer that we've used. They wanted to provide a single sign-on authentication for their network and for their SAP applications, and they wanted to administer the security policy based on their user's role. They used Intersys's user personalized network single sign-on. The user authenticated via token or a smart card, and basically that was seamless login to their network infrastructure. So benefit basically, policy administered on the business role, very effective management of central resources, and change management was very easy. If you want to come down and see how this works, we have it set up downstairs, and we'll have it here tomorrow as well. Another customer was a university in the US, College of William and Mary. They were getting a problem with Weltia, the worm that was coming out, and basically what were having problems with was the students were having infected laptops connecting to the university network and then infecting everybody else in the network. So the solution was the secure network infrastructure, and using the policy manager, we very quickly managed to reconfigure within one click 650 switches that stopped that worm from ever entering the network. Okay, so the customer didn't have to worry about it. Baylor University, basically they have a lot of users. They wanted to have an acceptable usage policy for students, and they wanted to do things like prevent rogue DNS servers, DHCP server, protection from DOS attacks. I mean, the universities are a haven for hackers. Okay? And it's the university administrator's problem to actually protect the network infrastructure from these types of guys. Now, I went to NTU in Singapore. Last time I put a sniffer on their network, there was like 150 hacks every second. It was absolutely incredible. They've got a whole load of Eastern European students there that are having great fun. Yeah? So, for those types of environments, we can push down policies to prevent it from ever happening. And then if we do detect something that we don't already have a policy for, we can dynamically respond to that particular policy. So in summary, secure networks, security is pervasive. It should be part of the entire infrastructure. The network infrastructure itself should play a part of the security policy. It's not a bolted-on approach. It's proactive. And what I mean by proactive is, there's this concept of false positives, but if I can eliminate the bulk of the traffic from ever entering the network in the first place, then I've eliminated a lot of those false positives. Very scalable and very dynamic. Okay? And we are starting to see, this bet that we made in the year 2000 or the year 1999, the R&D track that we've taken over the last 3 years is actually becoming something that customers are asking for. So we made a pretty good bet, I think, 3 years ago. So that's the end of my presentation. Security embedded throughout the network. Is there any questions? Did I finish on time? No? Okay, if there's no questions, then I thank you for your time. And if you want to drop by the